So it's a pleasure to welcome Dominic else here. I think this is the first time in Princeton.
First time at IAS.
First time at IAS. Yeah, I hope there will be more, but he will be here the whole week, so if you have any more questions, we can discuss it then. I plan to ask many questions.
Yeah, let's see how much I get through the talk.
So you can see the title and the name. Will go to dinner. If you're interested, please send me an email because I need to make a reservation because the group say send me an email by 4 and I will make the reservation. Again, dinner, please let me know by 4.
Yes, thanks. So it's great to be here for the first time. So I'm going to tell you about this paper we put out recently. So, okay, so we want to talk about symmetries, and of course, both in quantum field theory and in quantum many-body systems, symmetry is, one of the most important concepts you can have. So in quantum field theories, if you have, it's focused on invertible zero-form symmetries. You have a global symmetry. How do you characterize that global symmetry? Firstly, obviously, you have a symmetry group, G. And then there's also an interesting property that you can have, which is the Hooft anomaly of that symmetry group. So for example, if you're in 1+1D, if you have a global U1 symmetry, you can have a Hooft anomaly, which is labeled by integers. And one of the manifestations of that is if you couple to a background gauge field, the charge becomes non-conserved. So like you get this kind of chiral anomaly, the charge is non-conserved in the presence of a background gauge field. And this is, there's this quantized coefficient, which is an integer. So in general, these Hooft anomalies are topological properties of quantum field theories. They're non-perturbative and discrete. This equation is very rigid, so it's not something that can continuously deform. And then anomalies have many consequences. For example, the result of RG flows, so that already gives you a lot of constraints. So let me just, since in this talk I'll focus more on discrete symmetries, I'll just give you an example of a Hooft anomaly for a discrete symmetry. So let's consider a global Z2 symmetry. And in fact, you can just consider in 1+1D this compact boson. And then if you think about how the kind of Z2 symmetry act on this compact boson, there's kind of two fundamentally different ways it could act. One of them is whether it just acts, it shifts the primary field by, sorry, not primary field, it shifts this compact field by pi. That's kind of a non-anomalous symmetry, but there's also an anomalous symmetry where it shifts both the field and the dual field also by pi. And these are fundamentally just different. There's no way to connect these two symmetries in any way. They're just different symmetries. And in the non-anomalous one, you can see that you can just turn on a cosine term for this dual field theta and drive the system out to a trivially gapped state. The anomalous symmetry, you can't do that. In fact, all the relevant terms you could add that would respect the symmetry, either they end up driving you to a gapped phase with spontaneous symmetry breaking. So the signature of the anomaly is actually you cannot have a trivial gapped phase. You can only have gapped phases once the symmetry is spontaneously breaking. Again, that reflects the invariance of the anomaly of the RG flows.
So what the relevant term here is?
So the second one, I think if you add again, I didn't think about this ahead of time. I think if you add cosine of, if you add cosine 2 theta, that would respect the symmetry, but it would have two different vector, corresponding to theta 0 pi. That would be spontaneous symmetry breaking.
Why wouldn't that be the same as the?
Well, you can also add that here, but here you can also add cos theta, which would drive you to a system with a single vector. You can have spontaneous symmetry breaking without anomaly, but the anomaly requires spontaneous symmetry breaking to open that gap. So there's anomalies in QFTs, and there's a lot that you can say about the structure of these anomalies. In this talk, I want to focus on lattice systems rather than QFTs. So why should we do that? Well, of course, if you want to lattice regularize your QFT, then you need to talk about lattice systems. I'm a really condensed matter physicist, allegedly, and in kinetic lattice systems, often, the kind of systems we want to study really are on the lattice, not on the continuum. And so if you want to study anomalies in those systems, you definitely need to study lattice systems. And later I will mention some more kind of concrete condensed matter applications. It turns out that lattice anomaly is actually very closely related to things like many-body localization. Maybe I'll get to that later. And then the other thing is just that it's easier. I mean, QFT is a very difficult thing, especially if you want to have any kind of like mathematical rigor to it. In a lattice system, you can formulate things very like explicitly and precisely. So we're able to get a very general understanding about, extreme technical difficulties. So how do we define anomalies of a lattice? The most important thing is that it's not a property of a particular Hamiltonian, it's a property of the symmetry, the way the symmetry acts on the degrees of freedom. Now, in some sense, I think this is supposed to be true in QFT as well, but it's maybe a bit harder to make precise what that would mean, I think. But certainly on the lattice, this is going to be true. The anomaly is going to be property purely of the symmetry. So for example, so let's consider a 1D lattice system, which is just like a spin chain, for example. You can act on that system with a symmetry, which is just a Z2 symmetry, where you just act with a Pauli sigma X on each spin individually. So that's like a Z2 symmetry. And if you have a Z2 symmetry, you can write lattice Hamiltonians with respect to that symmetry. In particular, you can write lattice Hamiltonians with respect to symmetry, which flow in the IR to a QFT with non-anomalous Z2 symmetry. For example, you can realize this compact boson with a non-anomalous Z2 symmetry. On the other hand, there's a different Z2 symmetry we can write on the lattice, which looks like this. So you again have this layer of sigma x's, but then in addition, you also do a controlled Z gate on each pair of neighboring spins. And so it turns out if you do this, and then try to write symmetric Hamiltonians of a lattice and say, like, what governs the IR physics of those Hamiltonians, they are always governed by QFTs which have an anomalous Z2 symmetry. So you see that the anomaly is really reflected in the way that the symmetry acts on the lattice system. So the difference between this and this, it should be reflective of some anomaly. So the goal is to like make these observations into some kind of systematic classification of anomalies. So let's take a step back and be more precise about what we mean by symmetry on the lattice. So let's start with just quantum mechanics. Quantum mechanics, you just have some Hilbert space, and then symmetry would be like the unitary operator that acts on Hilbert space. It would be anti-unitary too, if you want. But I'll just focus on the unitary case in this talk to make things simpler. So that's a symmetry, and then if you want that's like one symmetry, but if you have like a group of symmetries, you should talk about representations. So if you have a group G, then you have a Hilbert space which the symmetry acts on, and then you have a homomorphism from the group G into the group of projective unitaries that act on that Hilbert space. So PU just means projective in the sense that we mod out by phase factors, so we can have projective representations. So that's the usual definition that we're familiar with in math of a representation. And so generally in quantum mechanics, symmetries act by representations of the symmetry group. But this is not the right definition for quantum many-body systems, even on the lattice, because this notion of a representation doesn't encode locality. For quantum many-body systems, you always care about locality. Locality is the most important thing. Everything has to incorporate locality. And so a representation, you don't know how it acts locally. So that's not the right definition of symmetry for a quantum many-body system. What you're interested in quantum many-body system is how does the symmetry act on local operators? So if you have some lattice system, some algebra of local operators. And so an element of that algebra is just some operator that acts on finitely many spins. Now, the important thing about this algebra of local operators is that is closed under linear combinations. The linear superposition of two operators is two local operators is also a local operator. It's also closed under multiplication of operators, and it's closed under adjoints. So that defines a property that mathematicians call a star algebra. So in this talk, we assume that A is this thing which I call an on-site algebra. So what do I mean by on-site algebra? It's a tensor product over sites. So there's some set of lattice sites, and then the algebra is a tensor product over those sites. And the algebra associated with an individual site is just the matrix, finite dimensional matrix algebra. So the algebra of ds times ds matrix. So ds is some finite number associated with the site. So basically, if you have a lattice system and you're not imposing any kind of constraints or anything, this is the algebra of all local operators you can have takes this form. So it's just like basically we're assuming like a tensor product over space, and then all local operators live in the algebra. So if you did the other things like impose constraints, then you would get an algebra which has a different structure to this. But for the moment, we're not considering that. And then we want to consider automorphisms of star algebras, isomorphisms. So if you have two star algebras, then an isomorphism between them is just a map that preserves all the structures. So you have a linear map, which means it preserves like linear combinations, linear superpositions, and then also preserve multiplication and adjoints. And it also has to be invertible, so it has inverse with the same properties. And then automorphism is just an isomorphism A to itself. And so basically my point is that a symmetry should correspond to an automorphism of the algebra of local operators. For every local operator, it should map it to another local operator, but that's what symmetry should do. In fact, that's kind of the definition of symmetry, is how it acts on the local operators. If you're wondering why, sorry.
There are also anti-unitary symmetries.
So that there are also anti-unitary symmetries.
Yeah, I mentioned I'm just considering unitary symmetries to keep things simple. You can obviously extend this to anti-unitary easily. You just say this map as the anti. Yeah, so if you're wondering, how does this relate to this definition I gave in quantum mechanics? Well, suppose in quantum mechanics, the algebra you would talk about would be the algebra of all linear operators on a finite dimensional Hilbert space. And then you can show that for any automorphism in algebra, it just corresponds to some unitary operator. Actually, it's just by conjugation by a unitary operator. So in the case of like finite dimensional Hilbert spaces like quantum mechanics, this concept of automorphism just reduces the usual notion of a symmetry is just a unitary operator. But the advantage of this definition is that you can do also like many body systems, even like infinite systems. But if you want, you can always think about these unitary operators, like if you consider some like finite approximate to your infinite system or something, that will automorphism will act by a unitary operator. But the important thing is that we preserve the notion of how it acts on local operators. And then there's one more condition which we want to pose, which is this locality property. So we consider an isomorphism with bounded spread. That means that there exists some finite R, such if you have some operator A that's supported on some set in R to the D, then its image under the automorphism has to be supported on some enlargement of that set. So if this is S, then basically this is S plus R. It's the set of all points which are within distance R of the original set. So if you have an operator that's supported on this region, it will get mapped to an operator supported on a slightly larger region. So in that sense, it preserves locality. So in this talk, I'm going to say that a symmetry should have this property that it's a local isomorphism. Of course, one could consider other symmetries which violate this. For example, like crystalline symmetries like reflection symmetry would violate this. But yeah, I mean, it's interesting to think about such symmetries as well, but for this talk, we'll just exclude that. And then there's this other name. If you have a local automorphism and it acts on this on-site algebra, so it's like tensor product algebra, these things have also been called quantum cellular automata, QCA.
Excuse me.
Yeah.
But if you have something where R is non-zero, you act again and again and again, aren't you eventually going to get something that's non-local?
Yeah, and so for example, translation symmetry would have that property.
Yeah.
Yeah, that's fine. We
So
used to
the
have.
group you're going to get is not going to act locally, right?
Yeah, I mean, often we will consider like finite groups, and that's it.
If it's a
finite groups like
finite-
that happen. But yes, in general,
I see.
we can consider
So if
groups where the range does like grow. For example, translation symmetry. But as long as like the generator has finite range, it kind of feels like enough.
I see.
So for translation, it's not completely non-local. You just shift the location of operator from here. It's still local.
That's not what his definition.
But it doesn't satisfy this
But
boundary.
if you consider T tensor T inverse, let's consider two Hilbert spaces. That's bad because you take a local operator and you might make it really non-local. You make a distinction between these two.
No, I
spaces.
mean, even that thing, the general classification I'll describe would apply to that too. There's actually some interesting examples of such, but yeah, we can talk about that later. Yeah, so there's this notion of quantum cellular automata. The name is maybe a bit obscure, but it really just describes these automorphisms, local automorphisms of the algebra. If you consider like, instead of these like quantum style algebras, if you consider like injective style algebras, you would recover the notion of classical cellular automata. I think that's maybe where the name comes from. But anyway, in this case, in this talk, we'll talk about this quantum cellular automata, QCA. So what examples of these QCAs? Well, any finite depth circuit will be a QCA. So, I mean, I'm showing this is the same picture I showed earlier. That's give us a finite depth circuit. So this is definitely QCA. So this obeys this definition of symmetry that I gave. In particular, you can consider like the case where you just have only the on-site actions. Often many of the symmetries we think about in physics are of that form. Like if you just have some spin rotation which acts on each spin, it would just be a product of the spin on each spin, the spin rotation on each spin. So certainly that also counts as a symmetry. But we can be more general, consider any finite depth circuit. It's not true that all QCAs are finite depth circuits. There's a kind of interesting classification. And for example, a translation operator, which we already discussed a little bit, that's certainly a QCA because it has finite range. I mean, the individual QCA has finite range. As it would just say the group generated different statement, but certainly a single translation has bounded range spread. But it cannot be written as, it turns out it cannot be written as a finite depth circuit. So it's an example of something that's beyond finite depth circuits. Anyway, so these are the main examples you can have in mind for this talk. There are some kind of also interesting QCAs that one could think about, but for most of the stuff I like to talk about, these two will be enough. And then we can talk about the concept of representation. So remember, in quantum mechanics, representation means you have a Hilbert space and then the symmetry acts on that Hilbert space. And also it's just a homomorphism from G into the projective unitaries on that Hilbert space. And so basically you can define like a high dimensional in the sense of a quantum many-body system representation. And instead of choosing a Hilbert space, you choose an on-site algebra. And then you have a homomorphism from G into the group of local automorphisms of that algebra. That's in general what I mean by a kind of many-body representation of the group G.
So are you only considering regular lattices? Because of course you could have, like this discussion here, you could have any set of points. Each having this.
Yeah, any set of
structure.
Any set of points is fine. Like so in this definition of on-site algebra.
There's QCA. That distance R, we could have any definition of distance.
Yeah, I mean, okay, I mean. Definitely the abstract definition of QCA makes sense basically for any like metric space. I mean, for most of the applications I want to discuss in this talk and also the general classification I will discuss, we assume that the set of sites is embedded in R to the D and that the distance is at least somewhat similar to the like regular Euclidean distance.
Okay, so you want your sites to be embedded in R to the D. Thanks.
Sorry, I have a really naive question. If I have a 2D lattice that implements 2D lattice with rotation symmetry, if I take S to be far from the origin, then it moves a lot. And
Yeah, if it doesn't satisfy this bounded spread, so that would be beyond.
so that you wouldn't consider rotation localized.
Well, under this definition, no. I mean, of course, I'm not saying it's not interesting symmetry to consider, but in this talk, we're considering like more kind of internal symmetries which don't do that. And then, yeah, just one point is that representations, like in quantum mechanics, you can take tensor products of representations, right? If you have two representations, then you can take a tensor product representation, and it acts on the tensor product algebra. Physically, it's constant stacking. You take two systems, each with a symmetry acting on them. So that's the definition of like symmetry, basically. But now, what about anomaly? The idea of anomaly is going to be some kind of, we want to say like, when do two symmetries have the same anomaly, or when do they have different anomaly? It's going to be a property of this symmetry action. And so how do we define that? Well, we can take some motivation from this observation about QFT anomalies. If you have some QFT with a G symmetry, these two QFTs have the same anomaly, if and only if, same anomaly for a group G, if and only if they exist in interface that's symmetric on the G. I don't think that, well, I'm told that this is not like something that's being proven. I believe it is true.
One direction is a conjecture. Right?
Anyway, so we'll sort of take it for granted that it's true. And by symmetric interface, I don't mean like gapped interface. So we're going to take inspiration from this.
May I ask a question?
Yeah.
So you said if and only, so that means that if anomalies are matched, there is always an interface. With what property do you have by requiring the interface?
I don't want to require any property other than it be kind of local quantum field theory, I guess.
G-symmetrical.
G-symmetric, yes.
This is an interface in space, right? Space is
In space, yes.
So for example, translation, what would you do? Yeah.
Translation.
You could do translation parallel to the interface.
No, I'm asking about translation.
Yeah, you could do translation that way. It would be
I
fun.
mean, one plus one dimensions. The interface is a point or some neighborhood. To move it. I want to see whether it satisfies this requirement.
If that wasn't the case.
This is continuum. You said you don't have any requirement. For example, if you rotate it in a timeline, so the interface go in the spatial direction, you don't require, so there is an operator. You don't require any property in the operator, except for the respect for the symmetry, which means probably you meant commute with G.
Yeah, I don't think we want any other.
Any operator. So for example, operator may not be invertible, for example, or may not be local, any properties.
Yeah, I think that's fine. Like, for example, if you want to connect like two TQFTs, usually the boundary is non-invertible, but as long as they have the same anomaly, that boundary exists. So I don't think you want to place any restrictions on.
Thank you very much.
So translation symmetry
Is this
somehow.
for internal symmetries or?
It might be for internal
Excluded parity and rotation.
Yeah, I didn't exclude translation yet. I think you're right that it doesn't, it's not so obvious that this statement works for translation. Okay, yeah. Maybe it's for internal symmetry. But the thing I'm gonna say for lattices, you actually can't do translations.
I'm confused. Can't you have a theory that has some anomaly and then you have some boundary and some boundary degrees of freedom that cancel that anomaly?
No, this is like a bulk anomaly. I mean, if you have like an SVT, it has an anomaly on the boundary, which can be cancelled by some degrees of freedom on the boundary. But if you have an anomaly in the bulk, that's a stronger statement. The only way to cancel that anomaly would be introduce extra bulk degrees of freedom, but then you're changing the QFT to something else. Yeah, so we're going to take inspiration from this observation to define our definition of anomaly on lattice systems. But because because as I said, in lattice systems, the anomaly is purely a property of the symmetry. So the definition will not involve any Hamiltonians. If the phrase is purely in terms of the symmetry. So consider two G reps, U and V. So G reps is just short for representation of the group G in this quantum many-body sense. And then there's this concept of a blend. So a blend from U to V is a G rep V, sorry, G rep W, which with these properties. So this is a picture of a spatial configuration. So this W has the property that you can divide the system into kind of two halves. On the left half, W of G agrees with U of G. On the right half, W of G agrees with V of G. So it's a blend. It's like blending between two different G reps spatially. And then we have this interface region where we don't put any constraints, except that we say that it has to be a G rep. So that still means that there's some composition rules that have to be satisfied.
This is continuous space, and you're requiring some degree of continuity across the gray region.
No, I mean, so this is like R to the D, but like we always assume that because the algebra they act is based on this lattice structure. So we assume that the lattice lives in R to the D.
There's no continuity.
No, there's no continuity in it.
The gray region is the same as R. The size of S to the R, the locality.
You can probably show that if a blend exists, it can have width R, yes, but I mean, we don't need to include that in the definition. Yeah, we just require any width of.
You're not allowing like exponential tails to bleed into the red and blue region where it kind of disagrees.
No, because like in a definition of local isomorphism, you require like this kind of strict version of locality. It's order S and it's ordered and its image is ordered S plus R strictly. So that's not compatible with exponential tails. There's probably some versions of these definitions that one could give that would allow, but it's a lot harder to give any rigorous proofs once you do that. So we just restrict it strictly to local case. Yeah, so this is on our concept of a blend. So if two G reps admit a blend between them, then we say that they are blend equivalent. And as we'll see, not all G reps are blend equivalent because there are obstructions to that. So that leads to our definition. So anomaly on the lattice is just an equivalent class of G reps under this blend equivalence. So two G reps have the same anomaly if and only if they are blend equivalent. That's our definition. And in particular, you have the trivial anomaly, which is the equivalence class that contains the trivial rep. In general, any on-site symmetry is also in this trivial anomaly class. And then lattice anomalies in D dimensions form a group, an abelian group, under the stacking, on this tensor product relationship that defines the group. I leave it as an exercise to the audience to say, why is it a group? In other words, how do you know you have inverses? Anyway, there is a proof you can give of that. So lattice anomalies define this abelian group, the stacking, and we will call this the abelian group of lattice anomalies of group G. So this is the lattice equivalent of the anomaly classification in QFT.
Could you give some indication of how you get the inverse? Usually if I have a representation, there's, I can find another representation so that the tensor product contains the trivial representation, but in general, it will contain other stuff So I'm not getting the inverse here.
Well, indeed, it's true that this being a group only works in dimensions greater than 0. Okay, I guess maybe I shouldn't leave the exercise to the audience. I can just tell you. So you use this, there's basically this folding trick. If you have a single G-rep, you can just take the space it lives on, R to the D, fold it in half. Now you get a blend from the original G-rep tensor its mirror image to a trivial rep. So the mirror image always gives you the inverse.
Okay, thanks.
So that's the definition of anomaly. So now, yeah, that's kind of a setup for what are we talking about here? And now the questions I want to address are, how are these lattice anomalies connected to QFT anomalies? Also, how do we classify lattice anomalies? And then, as I said, the anomaly is defined without reference to any Hamiltonian. But if you did have a Hamiltonian that was symmetric under that anomalous symmetry, what would that tell you? But these are the kind of questions I want to answer in this talk. So the answer to the first question, what is the connection between lattice anomalies and QFT anomalies? So I claim that the answer is the following. So there is a homomorphism from lattice anomalies to QFT anomalies. The lattice anomalies here are defined in the way I discussed. QFT anomalies, however you like to think about QFT anomalies, you can probably construct this group. However, this map is neither injective nor surjective. So lack of injectivity, what that means is there are elements of the group of QFT anomalies which cannot be realized as images of lattice anomalies. In other words, there are QFT anomalies that cannot be realized on the lattice. That's a fairly well-known statement. For example, in one spatial dimension. So here when I write D, I always mean space dimension. Sometimes this leads to confusion talking about INT theorems. So D is always spatial dimension, not space-time dimension. So in one spatial dimension, with a global U1 symmetry, you have this chiral classification of anomalies, which is the Z, which is the chiral anomaly. It's the equation I gave at the start. And then what you can show, should have had the citation for this result, but this paper by Kapustin et al. Where they should show that the global U1 symmetries, the lattice anomalies actually have trivial classification.
That must assume something, because there are examples where the lattice model does have an anomaly.
Are you talking about this thing that like Schuhan did?
Sorry?
Are you talking about this model like Schuhan?
I'm talking about even earlier things, like you have modified Villain for.
For modified variant, I mean, I think at some point we discussed this before. It's this lattice model of space-time. If you actually try to construct a maybe I'm thinking of something else. I think maybe the stipulation here is that it's finite dimensional over space beside. I think maybe that's the part that doesn't work for this modified variant because it has like some rotor.
There is an example in Schwinger model where there is some group of chiral symmetry which is anomalous.
That's the lattice model.
It's a lattice Hamiltonian where you have a unit translation.
He excludes translations.
He excludes, I see.
Well, I don't exclude translation in terms of symmetries, but translation is not a U1 symmetry, right? It's a Z symmetry.
A translation in that case turns out to be a chiral rotation.
So in the IR, it becomes a U1 symmetry, but that's fine. But here, when I mean lattice anomalies are U1, I mean you actually have a U1 symmetry on the lattice.
You also have finite dimensional on-site inverse space.
Yeah, that
With sugar model is order.
Okay, well, yeah, that might also.
Why do you pose this multi-dimensional space?
Well, I mean, I don't know. I mean, in lattice systems, often the systems of interest have finite dimensional open space, but
Like the harmonic oscillator, hydrogen atom.
Yes, well,
They do not have a finite dimension.
yes, but spin systems, for example, would have this. I mean, it's certainly an interesting question to extend these classifications to infinite dimensional Hilbert space. And I think the general structure I described later is probably going to apply, but the QCA classification is going to be different. That will lead to different classifications. Yeah, so if you have an infinite dimensional Hilbert space, its lattice anomaly is probably different. And that's an interesting problem to consider too. But yeah, for the moment, I just consider finite dimensional Hilbert space. Anyway, so you see that because lattice anomalies are 0, obviously these QFT anomalies are not in the image. So these are QFT anomalies that cannot be realized as a U1 symmetry inputs. And then lack of injectivity means that there are non-trivial lattice anomalies that map to trivial QFT anomaly. So I won't give an example yet, but we'll see in the course of the talk examples of that. And so note the difference with UV-IR matching of QFT. So there's a sort of similar thing that one could do, which is that you have a UV QFT with global symmetry, and then you have an RG flow to an IR QFT with a symmetry. And then there's a anomaly matching that you can do. But if it's the case that the UV symmetry and the IR symmetry are the same, I mean that's not always true, but suppose that was the case, then the UV anomalies and IR anomalies are into one-to-one correspondence, right? But that's not true if the UV is a lattice system, the IR QFT. That's what this equation tells you. The physical interpretation of this map is that you take a lattice system and then you consider the QFT that starts the IR physics of that lattice system. But the anomalies are not in one-to-one correspondence in this case. So yeah.
The continuum case, just RG from UV to IR QFT. Isn't the arrow in the other direction? So we have a UV symmetric of GUV and IR symmetric of GIR. So we have a homomorphism from GUV to GIR. But then for the anomalies, we have to pull back, right? Because they're given by some topological.
Well, I mean, this is kind of assuming that the symmetry, it's the same symmetry UV. In that case, that arrow you discuss is an isomorphism, so it can have an inverse as well. But I kind of back up slide up this.
Wait.
Well, no, not over here. I mean, I'll just say, but so if you have a UV QFT with some symmetry and some IR QFT, then there's a homomorphism between them, and then. Sorry, this equation is wrong. This equation just say alpha is psi star beta. So the UV IR, the UV anomaly is the fullback map applied to the IR anomaly, and that's what you were saying about the arrow. It's not this phi that was not supposed to be. And then the statement in the lattice system is similar, but yeah, and now you have this phi map. So this phi is a map from lattice anomalies. Yeah, from lattice anomalies into QFT anomalies of the same symmetry group. And then you also have this pullback map. So there's a consistency condition now which has to be satisfied. That's a statement I wanted to make. So this is again different because here, if I had gone to the equation right, there would be no phi. But here, there has a phi. That's the difference. So now, I want to talk about how to do the classification, and then we'll see some examples kind of emerging special cases like this. So the first thing to talk about is the classification of QCAs. So this slide looks almost the same as the slide I had before, but I'm talking about QCAs, individual QCAs, not representations. So if we have two QCAs, I say they're blend equivalent if there is a QCA W, such that W agrees with U on one half of the system, agrees with V on the other side of the system. That defines blend equivalence. And again, blend equivalence of QCAs form an abelian group. And then the group operation, you can think of it either as tensor product or as composition of QCAs, it doesn't matter. And then, so you can try to classify this abelian group in various dimensions. I mean, you can do fermionic or bosonic systems. And we just focus on the bosonic case. Fermionic fermionic versus bosonic in the lattice context is a statement about the structure of algebra local operators. In a fermionic system, the operators anti-commute if they have fermionic pattern -1 even at large distance. But yeah, so in the bosonic case, there is this nice theorem from GNVW, which says that the classification of QCAs in 1D is actually this Q times. So this is the positive rational numbers, and then the times indicates that the group operation is multiplication. Then in 2D, there's this theorem that the classification of QCAs is actually trivial. And in 3D, it's not really proven, but it's believed that it at least contains a Z8 subgroup, which is related to the Witt group of 2 + 1 dt. Anyway, so most of the results, specific results I will describe in this talk, or specific examples will be related to this one QCA classification. So let's just try to understand what this Q times mean. So an example of a non-trivial QCA is a translation. So you have this translation QCA, and then the local Hilbert space dimension at each side has dimension D. We assign it an index, which is D. And you view that as an element of this group of multiplicative rational numbers. And then if you do like translation by n sites, that would have index D to the n. Or if you do translation by n sites in the other direction, it would have index D to the -n. And then if you stack different if you stack these translations of like different local Hilbert space dimensions, you can build any rational number this way. That's kind of where the rational number classification goes. Basically, the non-trivial QCAs are just these shifts. And then you can try to convince yourself, why is this translation not blend equivalent to a trivial one? You sort of imagine if you try to like have this translation being blend equivalent to a trivial. So here it acts with translation, but then here it acts trivially. You're going to see something's going to go wrong because your particle moves along and then kind of has to get stuck here. So there's no way for it to go. So that's why this blend cannot exist. So now, given this classification of QCA, you can try to construct invariants of the G-reps, which is
Sorry, is the map to the index, is that supposed to be a homomorphism?
So you're asking about this slide?
The index, you have this index from a group of QCAs to an index. Is that supposed to be a group homomorphism to the?
Yeah, it's a group homomorphism, sure.
Can you describe the QCA which has index 1 over D?
It's just the inverse of this translation. The translation to the right would have index D. If you do D inverse, it would be translation to the left. Is that clear?
So translation to the left has index 1 over D?
That's right, yes.
Okay.
So given a G-rep, a G-rep is a homomorphism from G to the local automorphism. But for each local automorphism, you can assign it an index in this QCA classification. So that means you get a homomorphism from G into the QCA classification. The homomorphism G into QD. For later generalization, you can also view this as an element of the first homology group. So if this homomorphism is non-trivial, then we definitely have a non-trivial lattice anomaly. Because if the G-rep was like blend equivalent to a trivial G-rep, then certainly each QCA appearing in the G-rep also has to be blend equivalent to the trivial QCA. And this homomorphism precisely is the obstruction for that blend existing. So anything which has this non-trivial QCA indices is going to be a non-trivial lattice anomaly. And so example of that is translation symmetry in D equals 1. So here G is just Z, and because translations are not blend equivalent to a trivial QCA, this translation symmetry we identify as having a lattice anomaly. And so now this is also an example of something that demonstrates the failure of injectivity, because certainly there's no QFT anomalies with this E symmetry of 1D. And the other way to see that is that this translation symmetry does a bit like a trivial product state ground state, right? If you just have a translation, you can easily construct translation invariant product states. So the low energy QFT description of that system would be completely trivial. There's no anomaly. So this is an example where the lattice anomaly, which is non-trivial, maps to a trivial QFT anomaly. But so that's one invariant of the lattice anomaly.
In what sense is this an anomaly?
Well, okay, it's an anomaly according to the definition of anomaly I gave. It's an obstruction to gauging. I didn't mention this, but if you have, in order to gauge the symmetry, you need to be blend equivalent to a trivial rep. So this thing is an obstruction to gauging. I mean, what's your favorite definition of anomaly?
Last week.
Yeah.
Well, we should first agree with the previous definition.
Well, no, because we're in a different setting now, right? I mean, we're not the previous definition was for QFTs, but now we're in lattice systems. So.
But if this lattice system is a limit, it's like a CFT, like a QFT, then like the definition.
Well, you might like to, but this definition does not have that property. But it is, I mean, the one thing I can say in QFT, people, when you ask people what anomaly means in QFT, I think there's maybe two definitions that people will give you. One of them is it's an obstruction to gauging. Or another one is that it's a means that a QFT cannot be like trivially gapped out. And in QFT, these two definitions seem to be equivalent. Internal symmetries, I guess. I don't know if that's important or not, but okay, let me show it. Let's restrict to internal symmetries. Translation symmetry is not an internal symmetry, but we'll see examples of internal symmetries later. So let's not worry about translation symmetry not being internal symmetry. So in QFT, we have this gauging, obstruction to gauging, or like inability to triply gap out. And these are at least believed to be equivalent. So if you want to generalize anomalies to lattice systems, you know, you have to pick one of these to be the definition, I guess. We picked obstruction to gauging, if you like. That's our definitions. I think there's a bit for that. Yeah, and so we could have picked a different definition, which was this.
I don't fully understand both senses. When you say gauging, you'll be talking to classical background gauge field or making it dynamical.
No, very classical background.
But at the cost of sacrificing a little bit of gauging variance, you can couple it to background gauge field. The only problem with the partition function is not gauging, but you can couple it to background gauge fields.
Yeah, but I mean, if it's not gauging, I mean, that is, it should be gauging, right? I mean,
no, but it's not, and it's important that it's not. And the failure of gauging variance is characterized in a very specific way. So it's not that you just fail and you can't. In your case, I don't even see how to start.
How to start what?
Coupling it to background gauge fields.
Oh, well, if the anomaly really vanishes, I think there is a prescription that one can give to calculate a lattice model coupled to that. But it doesn't work when the anomaly is present. At the lattice version, I mean, gauging is certainly, background gauge field is certainly like a well-defined thing that often do on low nodes. You just introduce like link variables valued in the gauge group, and then the Hamiltonian just has to be modified depending on the configuration of those link variables. There's a standard procedure to do that, but it doesn't work if you have this anomaly. That's a statement.
Can you elaborate more about why the obstruction to gauging is related to the absence of random equivalence?
Yeah, so there's somewhere I can draw on the board. If all the audience can see it, I can draw it here. Yeah, so what does gauging mean? In order to, a minimum condition for gauging, you have to be able to act with a symmetry. There should be a meaningful concept of acting with a symmetry locally. So originally symmetry acts on the whole system, but you want to be able to take any subregion that acts with the symmetry on that subregion. Any concept of like gauging or even background gauge fields is going to require you to be able to do that. And blend equivalence is precisely capturing the obstruction to that being possible, because yeah, you can imagine. I mean, a special case of this would be like where you just try to act with the system on half of the system. So the system simply just acts on one half of the system. And that is precisely describing a blend between that symmetry and the trivial symmetry. So if your symmetry is not in the trivial blend equivalence class, that means that this kind of restriction process is impossible.
So that the blend equivalent just means that this interface between left and right has to represent G symmetry, but is it? How is it related to the?
Could you speak up?
Sorry, yeah, like I thought the blended equivalent just means that there must be some G symmetry preserved the interface between left and right. But is it really related to the obstruction?
Well, it has to act like the original symmetry here and act like the trivial symmetry here. I'm not sure what I mean. The interface is where it's not really constrained, except saying that it has to be a G-rep. The definition of blend is defined in terms of how it acts here and how it acts here.
That's not the same as adding a symmetry defect.
It is very closely related, because if you
But locally, the two sides look the same. You have a symmetry defect.
well, that's when you act on a symmetric Hamiltonian, right? If you want to create a symmetry defect, then I mean symmetry defect is defined more with respect to Hamiltonians. So if you did have a Hamiltonian and you acted with this object, the Hamiltonian terms on the right would be not acted upon, because the symmetry acts the same as the bulk symmetry, the original symmetry, and Hamiltonian is assumed to be symmetric. And the Hamiltonian on the left also would not be acted upon, because you're acting trivially there. So the only Hamiltonian that will be modified will be the ones along the interface.
There are cases where there are anomalies on the lattice for discrete symmetry. And you can form a interface, a symmetry defect, which is topological.
Yeah, but then there's some like higher like F, like there's some F move that has some phase back. I mean, there's always some signature of the anomaly, right?
But there is a signature, but it's there is a symmetry defect. Probably also your blending. There is an anomaly, and it coincides with the field theory anomaly.
Well, the fact that we impose that this G-rep, blending G-rep has to be, the blend has to be actually a G-rep, I think is a strong condition. I think in this case, if you consider something like this, but you didn't impose that the blending has to be a G-rep, then you can construct symmetry defects that way. But the fact that the defects ultimately have some kind of signature of the anomaly will be related to the fact that like this blend wasn't really a G-rep. So if you can construct these blends where the blend actually is a G-rep, I think that will give you symmetry defects that are non-anomalous. So this H1 thing gives you one obstruction to gauging. Oh, sorry, well, I guess it is an obstruction gauging by what we said, but one obstruction to having a symmetry which is blend equivalent to a trivial rep. But there are other obstructions. So suppose this first invariant vanishes, and it's true for each G, this QCA U of G is in the trivial blend class, which means it admits a restriction. So this is basically constructing a blend from U of G to the identity. But this blend might not be a G-rep. And what do I mean by that? What would it mean for this blend to be actually a G-rep? It would mean that you have this composition rule. So U of R of G1, U R of G2 would have to be the same as UR of G1, G2. That's the definition of being a G-rep. And is this going to be true in general? Well, no. But what you can say is that if this equation is evaluated, it will be evaluated only up to terms that act on the boundary. Because over here, U of R of G is agreeing with U of G, and U of G was assumed to be a G rep. Over here, U of R of G just acts like the identity, which is G rep, trivial G rep. So the only way this equation can be evaluated is by something that acts on the boundary. That gives you this definition of this omega G1, G2, which is a QCA that acts only near the boundary on this region here. And in particular, so U of G was like a d-dimensional G rep, or we can just take G equals 2, it's like what this picture is showing. But then omega is actually a one-dimensional QCA. So we can define the one-dimensional QCA class associated with this omega. I call it omega G1, G2. So if you start with 2 dimensions, this will be a one-dimensional QCA. In general, it's valued in UT minus 1. In particular, that gives you an element of the second column.
Will you discuss the relation of this to the on-site ability? Or this class also showed up in these papers?
Well, we conjectured that blend equivalence and that blend equivalence to trivial rep is equivalent to on-site ability. That's actually kind of hard to prove. I mean, you can prove one direction easily, which is that on-site ability implies being blend equivalent to a trivial rep. So on-site ability definitely implies like trivial blend equivalence class. The converse is very difficult to prove. But yeah, we believe it's probably equivalent. But certainly all these invariants, all these cohomology invariants that we construct are invariants both of blending and of this on-site ability equivalence. So at least as far as these cohomological invariants, everything seems to be equivalent. Yeah. Does that answer the question? So you have this invariant valued in H2 G Q minus 1. So for example, for a concrete example, you can consider G equals Z2 and B equals 2. Then remember QT minus 1, Q1 is just the one-dimensional QCA classification, which is just like multiplicative rational numbers. If you compute this H2, you'll find that it's basically Q times mod Q times squared. It's actually infinitely many copies of 2. That gives you this lattice anomaly classification in this case. And so indeed, you can explicitly construct G-reps that realize all of these classes. So for example, see this paper by Shori et al. So another important point is that these anomalies all descend to trivial Hooft. In fact, for G equals Z2 in D equals 2, there are no QFT. So that's obvious. Another consequence of that is you can actually find a product state that's invariant under this symmetry that they showed that in this paper. So again, this is an example of a Lattice anomaly that descends to trivial QFT anomaly. And in this case, it didn't require translation symmetry, it's just an internal symmetry. So the story so far is we have an invariant value in this H1 GQD. And then I showed that if this vanishes, there's an invariant value in H2 GQD minus 1. You're probably starting to see the pattern. So the general story is that you have this H1 GQD, H2 GQD minus 1, and then down the chain, HD plus 1 GQ0. And then the very last one is this one, HD plus 2 GU1. Turns out like minus 1 dimensional QCA is basically just like a phase factor. So if you know about spectral sequences, you can look at this technical note, otherwise don't worry about it. Yeah, so there are all these invariants that are related to the QCA classification and also the symmetry of G. And some of these will map to QFT anomalies. For example, this one probably will, because we know that there are QFT anomalies that in general classified by this root cohomology. Some of the other ones also map to non-trivial QFT anomalies, but some of them map to trivial QFT anomalies.
Is there some part that maps to some gravitational anomaly or some mixed gravitational things?
Yeah, I'm gonna get to that later. Yeah. But I should check out. It's already even.
It's over, but since there were lots of questions, I'm keep for a while, not too far. There are also cookies that people might want to get, so that's cut off.
So gravitational anomalies. Gravitational anomalies are reflected in the algebra. There's no symmetry. They're reflected in the nature of the algebra of local operators. We had this on-site algebra, which is just like tensor product of matrix algebras. But now we want to consider like more general algebras of local operators, and these will encode gravitational anomalies. But you need to encode this kind of locality structure. So this concept of a net of algebras or an algebra for each bounded subset of R to the D. Basically, for each subset of R to the D, there's some set of local operators. So it defines a locality structure, and there's some consistent conditions that we impose. So basically, we say that two local algebras are equivalent if they're equivalent up to tensoring of on-site algebras and up to local isomorphism. So tensoring of on-site algebras, kind of view the on-site algebras as being like trivial in the context of anomalies, and then tensoring with these algebras. So tensoring with these algebras is an equivalence, and also like local isomorphism is an equivalence. So then equivalence class of this local algebras under this equivalence equation form a monoid. And then it's a monoid because in general it doesn't have inverses needed in monoid. But if you focus on the invertible elements, that forms an abelian group. And we basically identify these as lattice gravitational anomalies. There's this really nice theorem from Hall, which is that lattice gravitational anomalies in D dimensions are actually 1-to-1 correspondence of QCAs in D+1 dimensions. So this kind of goes back to this, although the symmetry anomalies also involve, if you say, collection in dimensions like QD, QD minus 1, QD minus 2. But the lattice gravitational anomaly is actually related to QD+1. So QCAs in one high dimension.
What is gravitational about?
Nothing really. I don't know. People use gravitational anomaly to refer to an anomaly. It doesn't depend on any symmetry. So that's the context in which I'm using it here.
There's no metric in the story.
Yeah. I also think that QFT gravitational anomalies are not really gravitational either. But
they are. They're about talking to a metric, to a background metric.
But a QFT, which is non-relativistic, still has gravitational. So, and then you can't really couple to a metric unless you do this like Newton compound or something.
There's no metric in this story.
There's no metric. No.
And there's no gravitational attraction.
No.
Okay.
But what we can say is that there is a homomorphism from lattice gravitational into QFT gravitational. And these ones, I guess, maybe in some cases, there is something gravitational about them. But this map is neither injective nor surjective in general, just like with the symmetry anomalies. And a nice way to understand this through some bulk boundary correspondence. So the lattice gravitational anomalies are related to QCAs in one high dimension. QFT gravitational should be related to invertible TQFTs in one high dimension, which are also supposed to be the same as classification of invertible topological phases. That's not something you can prove easily. That's believed to be true. So this map, you can also think of it as a map from QCAs in D+1 dimensions to topological phases in D+1 dimension. And the map is basically just a evaluation map. So if you have you just take a fixed product state, act on it with QCA, that defines a map from QCAs to invertible topological phases. I think that's kind of the cleanest way to think about this where does this map comes from. It's because not all invertible topological phases can be created by acting with a QCA. And secondly, not all non-trivial QCAs create non-trivial invertible topological phases. Right? That's why this map is neither injective nor surjective. And if you want to do something like this, there's a version of this story also for symmetry anomalies. We do consider like symmetry enriched versions of these statements. Okay, let me skip over that. There's some interesting connection to these width classes, but I don't want to go into that. So if you do have a lattice anomaly, what are the consequences of that? For Hamiltonians that are symmetric. What's definitely not true is that lattice anomaly does not necessarily imply that you cannot have a symmetric trivial ground state. So we saw many examples of that, like translation symmetry admits a product state ground state. Generally, like these like lattice anomalies that map to trivial QFT anomalies, they usually, or probably always admit like trivial ground states. But it does imply some other interesting things, like a lattice anomaly does forbid trivial symmetric commuting projector models. It also forbids trivial many-varied localized phases. There are interesting physical consequences of these lattice anomalies, even in the case where they map to trivial QFT anomalies. And then there is a subset of lattice anomalies, namely the ones that map to non-trivial QFT anomalies that do forbid symmetric trivial ground states, if not all structured. So where do we go from here? I would like to extend this to QFT. I mean, QFT, maybe there's some ways to understand anomalies, but they're not phrased in this like operator algebraic sense. So it would be nice if there would be some way to do that. So QFTs also have some like algebra flow properties. We call that algebraic quantum filtering. And then symmetries definitely should be local automorphism in that algebra. The thing that's difficult is like what the generation on on-site algebra. Like there's a very clear notion of a lattice system, like what the most trivial kind of algebra is, which is this tensor product structure. But that doesn't have an obvious handle in QFT. But I would like to think more about discussing. And then what else can we do? Well, I focused on invertible zero form symmetries. So obviously we would like to generalize the non-invertible symmetries, higher form symmetries. More generally, I'd just like to classify these like local algebras. So the invertible ones correspond to gravitational anomalies, or lattice gravitational anomalies, as I said. But the non-invertible ones, you should be able to classify them too. And it's very good classifying the kinds of like local, if you think about like locally constrained systems, I think that's kind of what we would be classifying if we consider these local algebras. I would also like to think about SymTFT. It doesn't seem like SymTFT, as it's conventionally formulated, can capture like these kind of anomalous lattice symmetries. So it seems like we need some generalization of SymTFT for that. My eventual ambition is to have kind of a grand unified theory of symmetries on lattice, which would incorporate all of these things and many more, maybe in some unified story. But yeah, that's for the future. For the moment, I will conclude.
Use the time and have questions. This is small. Yeah.
So you were just mentioning the symmetry on the lattice. If you have, for example, LSM type anomalies, those you can sort of encode and enrich topological orders and study these the anomalies for those in that context. So are you thinking of really producing a D+1 dimensional, or for you two-dimensional QFT, but now lattice version of that, or what is sort of the picture they want?
Right, I don't know, because these LSM anomalies you mentioned are actually an example where it does map to
That's right.
onto a QFT. So that's why it would be captured by like a conventional SymTFT. And for these lattice ones, I think I have this idea that maybe instead of constructing like a TQFT, you should construct a commuting projector model on the lattice. It seems like that and can capture the more general things.
Just a quick question. So for the gravitational anomaly, is there something like for the continuum case? I guess it's not related to the factorizable validity of the Hilbert space.
Well, I mean that is kind of the lattice, what the lattice statement is too, right? Because we're saying that the on-site algebras, which are the ones where you just factorize into like a tensor product on each side, those are the ones that are trivial and have no gravitational. So the ones which are non-trivial are the ones where that's not possible. So yeah, it does seem to be related.
It should be considered as an equivalent statement.
I guess so. I'm not too familiar with this like quantum filter version of this thing, but I should look into that.
I have one more question. So the slide one before last, you focused on whether the symmetry is on site or not.
I don't know which side.
Well, one before last, the last one you showed, one before that.
The last one I showed at the end of the talk, the last one.
Yeah, at the end of the talk.
I still have no. This one?
We discussed the, not, the on-site issue. Is that the last one you showed? Anyway, there are examples where whether a symmetry acts on-site or not depends on the duality frame. There could be a mixed anomaly, say, between an on-site symmetry and not on-site symmetry. And there's another way to formulate a model where you swap the two. So the notion of symmetry being on-site is not invariant.
You mean in the context of the lattice system or in QFT?
In lattice model, well, in CFTs, there's no on-site, there's no site.
Well, it's a question of non-invariance under what? I mean,
The statement that symmetry acts on-site sometimes does not have an invariant meaning, because you can.
no, I mean, it's invariant under the blend equivalence or under, like, there's definitions one can give where it is invariant, but I think you're thinking of a more general notion of duality. I think the point is that in general dualities, they act not on the full algebra of local operators, but only some sub-algebra. So you say, basically it's saying that the symmetries are not distinguishable if you look at only at that sub-algebra. I think that's the statement. So maybe there are interesting cases when one should do that, but.
I have a tensor product Hilbert space and I have a symmetry that does not act on site.
Yeah.
Then I'm making a change of variables and then it does act on site.
No, there's no local transformation of that
There's
algebra
no local, but
that
it
will
is
not.
Yeah, but it is a local, but it is a valid relabeling of.
I think it's general, these dualities are local automorphisms, not of a full algebra, but of a sub-algebra.
So
So
for the full algebra.
There is a notion of unsidable, that's more invariant.
That's more invariant.
Yeah, so it's.
now unsidable is, this is invariant. I was saying things that unsidability is invariant.
Yeah, but to address Natty's question, I guess there is an equivalence that you said you impose two symmetries to be unsidable if we could add ancillae and do this change of variables. If we
But
did
then
that.
without ancillaes, in the Levin-Gu model,
This
the
is
change
always-
of variables adapts the model, or it does not act on site. Well, we've done way over time, so. Like that. I do remind you that we're going to dinner and please send me an email by 4. You have 16 minutes to do it if you're interested.